Okay, so hold on. All right, so I'm going to get started.
All right.
The fall season is shaping up to be a wacky one. We've seen some early snowfall and record cold in the Rockies, heat records broken across the east, extreme winds in the west. Now we're preparing for a cold front that could bring snow as far south as Tennessee. But are these extremes connected? We have Dr. Noah Diffenbaugh and Dr. Michael Mann here to help explain the weather extremes we're seeing. But first, we will have you introduce yourselves. Can we start with Noah?
My name is Noah Diffenbaugh. I am a professor and senior fellow at Stanford University.
Mike?
I'm Michael Mann. I'm a professor at Penn State University, where I direct a center for climate research called the Earth Systems Science Center.
Awesome. So first question, October's weather set records for heat, cold, rain, and snow in the US. Is this what climate change looks like?
Well, I'm happy to take a stab, and then Noah. You know, as I've said in recent years, with the unprecedented weather extremes we've seen, many of which have been extreme summer weather events, heat waves, wildfires, etc. But we're also seeing increases in extremes during the fall and winter and spring. And there as well, there is a signature of human-caused climate change. It turns out that the unusual warming of the Arctic actually appears to be influencing the behavior of the Northern Hemisphere jet stream in a way that gives us those larger undulations where you see big peaks and troughs in the jet stream. That means there are big weather systems underneath, high pressure systems or low pressure systems that give us heat or drought or excessive rainfall. What we're seeing is that these changes in the jet stream are leading to increased weather extremes of various types. Now, we're still trying to understand all of the mechanisms that may be involved. And my own research is really focused on mechanisms that relate to extreme summer weather events, persistent extreme summer weather events. But we're also seeing increases in some of these extreme winter events, and that involves a different set of factors from the ones that we've worked on.
Yeah, I think, you know, amplifying what Mike said, you know, we can think about, you know, changes in extremes due to climate change from the perspective of at least two components. And, you know, the first component is that we are adding heat to the climate system. And so scientists call, you know, that thermodynamic effects, but really it just means that the added heat in the climate system is increasing the energy that's going into heat waves, increasing the water vapor that's in the atmosphere, so that when we get these atmosphere and ocean conditions that have always occurred on Earth, in terms of just the weather patterns that have always occurred on Earth, there's now an elevated risk of extremes from the extra heat that's been added to the climate system. We see this in heat waves. We see this in heavy rainfall events. We see this in storm surge flooding from the elevated sea level that has resulted from that added heat to the climate system. So that's one pathway by which global warming is influencing extremes. Then the second pathway, which is Mike says an area very active, how those and how those are being influenced by global warming and the associated changes in the climate system. And Mike has done work on this. My group has done work on this. A number of other research groups around the world have been analyzing how, say, the warming of the ocean affects the atmospheric circulation, how the loss of sea ice that Mike described affects the atmospheric circulation. We are seeing signatures, for example, here in California, the frequency with which these ridging patterns that, for example, are occurring right now, that are creating warm conditions in the west and then associated colder conditions in the east. That ridging pattern in the Northeast Pacific and Western North America is happening with increased occurrence. And you know, in our research, we've identified the pattern of warming in the lower and middle atmosphere as the primary driver of that change in the atmospheric pressure pattern. So that's one example of that line of research.
Yeah, just to follow up on what Noah said. So some of these factors are pretty basic, right? You warm up the planet, you're going to have more frequent and extreme heat waves. That's a given. You're going to put more moisture in the atmosphere, so you can get larger rainfall events, worse flooding events. You're going to bake the ground, you get worse continental drought. You take that heat, you put it together with drought, you get wildfire. So some of this is fairly basic, and the mechanisms are captured well by the climate models that we used both to study the present and past and to project into the future. But some of these other mechanisms, as Noah alludes to, these dynamical mechanisms that relate to the behavior of the jet stream, that's still really at the forefront of current climate research. And some of the mechanisms that we think are important here don't appear to be well captured, at least in many of the climate models. So this is a reason for caution. There is a sense in which we may actually be underestimating the impact of climate change on some of these extreme weather events because of these more subtle connections that have to do with the jet stream, where we're still trying to understand them and they're still not perfectly represented in the climate models. I'll make one other point here as well. So there's certain very robust features of climate simulations that have stood the test of time. Decades ago, even the crude climate models that we were using at that time predicted that the so-called Hadley cell circulation, we have rising motion near the equator and sinking motion in the subtropics. And when you have that sinking motion, you get dry, hot conditions. Well, the models predicted that human-caused warming would actually cause a migration of that descending branch of the Hadley circulation. If you like, the belt of deserts moves further into the mid-latitudes. And so the fact that we're seeing unprecedented wildfires right now in the subtropics of the Northern Hemisphere, California, and the subtropics of the Southern Hemisphere in New South Wales, Australia, and Queensland, Australia, that is symptomatic of a pretty robust prediction that those areas get drier and hotter. And when you get drier and hotter conditions, well, you get wildfires.
Thank you. Another major record set in October was Arctic sea ice extent. It reached its lowest point on record for the month. Surface temperatures in the Arctic have been way above average. I'm wondering if the record heat and melt in the Arctic is connected to record cold that we're seeing in the United States.
Well, I think first and foremost, it's important to emphasize that the loss of Arctic sea ice is one of the most profound changes that we're seeing in the climate system. And when you analyze the statistics of the loss of Arctic sea ice, it's just phenomenal. I mean, statistically phenomenal. It's essentially impossible from a statistical perspective to have the level of decline that's occurred without this long-term forcing from human-caused climate change. So first and foremost, we know that very high confidence that the heat that is being added to the climate system through human emission of greenhouse gases, that by warming the atmosphere and warming the ocean, that's causing a very rapid decline in Arctic sea ice. It's literally, statistically a new normal, in terms of, the range of summer sea ice levels, and now we're seeing autumn sea ice levels as well. That new range is completely removed from the historical range. Just over the last 4 decades, we're now seeing that even the highest sea ice years in the Arctic are lowest than what used to be the extreme low, and we're really approaching. The prospect, the very real prospect of the Arctic being seasonally ice-free within the next few decades, which is something that scientists had predicted.
Yeah, just to add to that, this is actually a very good example of where the predictions have in some sense been fairly conservative. So we've seen Arctic sea ice decline at a rate that exceeds what the climate models tended to predict. And as our understanding improves, we recognize that there are certain processes that are relevant to understanding, the way that sea ice reacts to changing wind patterns that weren't well captured in the climate models. And as scientists, as climate scientists start to try to account for these processes, we're doing a better job. But still, the observations appear to be ahead of the models. We're seeing a decline in Arctic sea ice that is beyond what the models tend to predict. And that underscores sort of a fairly widespread theme here, that uncertainty is not our friend. Uncertainty can cut against us. And in this respect, it appears to be cutting against us. And there are surprises in store. And one of those surprises, stuff that NOAA's worked on, my group has worked on, our good friend Susan Joy Hassel likes to say that what happens in the Arctic doesn't stay in the Arctic. And that is absolutely the case here. We're seeing that these monumental changes in the Arctic, the warming of the Arctic and the loss of the sea ice in the Arctic, it appears to be changing the pattern of the Northern Hemisphere jet stream in a way that gives us these various types of persistent weather extremes that we've been experiencing both in the summer and the fall and in the winter. And so all of this is tied together. And if we tend to underpredict one change, there's a good chance that we are going to underpredict other changes because of the interconnectedness of the system.
Thank you. So more generally, are we saying or trying to say that the U.S., the eastern U.S. is frequently seeing cooler temperatures relative to the warmth and warming that we've observed globally? Sorry, tongue-tied today.
So that's a question that my research group has worked on, and we've worked on particularly this this juxtaposition of warm conditions in the West and cold conditions in the East during the winter. And that's essentially that the atmospheric setup that we're experiencing now in the US. So this is work that Professor Deepti Singh led when she was a PhD student here at Stanford. And what Deepti found was that the frequency of occurrence of warm conditions in the West and simultaneous cold conditions in the East, that simultaneous occurrence has been increasing over the last several decades here in the US. And in terms of the mean temperature change, what Deepti found is that the West has warmed more rapidly than the East. The East has warmed during the winter months relatively gradually. And the juxtaposition of the warm West and cold East events is associated with a very distinct atmospheric circulation pattern with high pressure anomalies over the West and low pressure anomalies over the East. And in Deepti's research, what she's found is that there's not yet a significant, statistically significant change in the frequency of occurrence of that pattern, although we do find an increase in the mean occurrence. But what's really key is that when that atmospheric circulation pattern occurs, it's much more likely to produce very warm conditions in the West combined with cold conditions in the East. So what we're seeing is the primary driver is the resulting temperature severity that happens when that atmospheric circulation pattern sets up.
Yeah, and let me add that, and I'm going to sound a little bit like a broken record here, because it again comes back to this issue of uncertainties, and uncertainties not really breaking in our favor. Surprises that are in store that aren't welcome surprises. And one of the things I've been particularly interested in is the intense nature of nor'easters. I live on the east coast of the US in the mid-Atlantic in Pennsylvania, and we are influenced by these extremely strong mid-latitude systems called nor'easters that have some of the characteristics of a tropical system. Like a tropical system, part of the energy that intensifies these storms comes from the heat released from the ocean when it evaporates moisture. And as we warm up the oceans, and we continue to get these clashes between warm sort of maritime conditions and the cold Arctic air masses that travel from west to east and eventually come to the eastern US and collide with the warm maritime air those temperature contrasts are what drive typical mid-latitude storms. So you've got these large temperature contrasts, which contribute to the strengthening of the storm, and you've got all this, what we call latent heat released from the ocean that's contributing to the energy of the storm. And it comes together to give us these fascinating systems called nor'easters. Now, we still don't model these perfectly. In fact, in most climate models, these sorts of storms are represented fairly crudely, just like hurricanes tend to be represented fairly crudely. And some of the emerging science, based on high-resolution modeling, looking at the characteristics of these storms, suggests that the warming of the oceans and climate change is increasing the intensity of these nor'easters. Now, what's interesting about that is these storms spin around, and when they spin around, they bring warm air from the south up on one side of the storm, on the east side of the storm, but on the west side of the storm, they bring this cold Arctic air down, and the stronger the storm, the more spinning. The more intense the spinning, the more intense the mixing. And the more intense the mixing, the more of that cold air you draw down. So it's sort of one of my pet theories that some of the extremes that we've seen in the winter along the US East Coast, and this really only applies to a particular region along the US East Coast, some of those cold extremes appear to be a product of these record strength nor'easters. And again, there's lots of uncertainty because we don't really capture these changes, these characteristics in sort of the large scale climate model simulations that are often done to project future climate change.
That's very helpful, thank you. And also speaking of things similar to hurricanes, out west, particularly in California, we've seen back-to-back surges of hurricane-like winds. This is the third year in a row that these winds have worsened wildfires burning in the state. Is climate change worsening their effects, and are these tied to any other weather patterns causing extreme temperatures?
So this is also an area of active research, and what's critical is that these winds combined with other conditions to create wildfire risk, and wildfires are a product of the physical conditions, the winds, how dry the vegetation is, how dry the atmosphere is when the winds occur, but also exposure and vulnerability and critically ignition. And more than 90% of the fires in California have a human ignition. So it's important to keep in mind that all of that comes together to create wildfire risk. And the conditions on the ground when those strong winds occur are really critical for the wildfire risk. And what we're seeing in California in recent years is we've had very warm conditions and very late starts to the wet season in California. What that has meant is that there are record dry vegetation conditions when these autumn winds blow. And so even without any change in the frequency or strength of those winds, we're seeing elevated risk coming from, again, the added heat in the climate system that's causing there to be higher temperatures in the summer and autumn. As Mike was describing earlier, greater aridity of the vegetation, this fuel aridity as scientists call it, but essentially the amount of dry vegetation on the landscape. And when that dry vegetation is combined with those very strong winds, that creates very high wildfire risk and very extreme wildfire behavior like we've been seeing in California in recent years.
Yeah, I can't improve on what Noah, has said. I think it's a very nice characterization and description of the problem. My elevator sort of speech version of this is, you take extreme heat, you take extreme drought, you put them together, you get wildfire. This isn't rocket science. What we're seeing now here in the United States and what we're seeing simultaneously in Australia right now is symptomatic of these changes that we predicted decades ago. Our predictions are coming true, unfortunately.
Thank you. Well, those are all of my questions. What is the best way for people to reach you if they have further questions?
I can be found on Twitter, on social media, Michael E. Mann at Twitter. My website is www.michaelmann.net, and I'm Michael Mann Scientist on Instagram. So come find me. I love talking about this stuff on social media as well.
Awesome. Noah?
My official work contact information is on my official work webpage.
Awesome. Thank you. And have a great day. Thank you for doing this with me.